Remember from Newton's law of gravitation that the gravitational force between two objects of mass m1 and mass m2 is proportional to the product of the masses and inversely proportional to the square of the distance d between them. The electrical force between any two objects follows a similar inverse square relationship with distance. The relationship among electrical force, charges, and distance, known as Coulomb's law, was discovered by the French physicist Charles Coulomb in the 18th century. For charged objects, the force between the charges varies directly as the product of the charges and inversely as the square of the distance between them. d is the distance between the charged particles. q1 represents the quantity of charge of one particle. q2 is the quantity of charge of the other particle. K is the proportionality constant. The SI unit of charge is the Coulomb, abbreviated with a capital C. A charge of 1 Coulomb is the charge of 6.24 times 10 to the 18 electrons. A Coulomb represents the amount of charge that passes through a common 100-watt light bulb in about 1 second. The proportionality constant K in Coulomb's law is similar to G in Newton's law of gravitation. K equals 9 billion Newton meters squared per Coulomb squared, or 9 times 10 to the 9 newtons meters squared per Coulomb squared. If a pair of charges of 1 Coulomb each were 1 meter apart, the force of repulsion between the two charges would be 9 billion newtons. That's more than 10 times the weight of a battleship. Newton's law of gravitation for masses is similar to Coulomb's law for electric charges. Where the gravitational force of attraction between a pair of 1 kilogram masses is extremely small, the electrical force between a pair of 1 Coulomb charges is extremely large. The most significant difference between gravitation and electrical forces is that gravity only attracts, but electrical forces may attract or repel. Because most objects have almost exactly equal numbers of electrons and protons, electrical forces usually balance out. Between the Earth and the Moon, for example, there is no measurable electrical force. In general, the weak gravitational force, which only attracts, is the dominant force between astronomical bodies. Although electrical forces balance out for astronomical and everyday objects, at the atomic level this is not always true. The electrical force dominates small-scale interactions and is responsible for all chemical reactions. Materials that allow electric charge to flow freely are called conductors. Metals are good conductors for the motion of electric charges because their electrons are loose. Electrons in other materials, rubber and glass for example, are tightly bound and remain with particular atoms. They aren't free to wander about to other atoms in the material. These materials, known as insulators, are poor conductors of electricity. The conductivity of a metal can be more than 1,000,000 trillion times greater than the conductivity of an insulator such as glass. In power lines, charge flows much more easily through hundreds of kilometers of metal wire than through the few centimeters of insulating material that separates the wire from the supporting tower. Semiconductors are materials that can be made to behave sometimes as insulators and sometimes as conductors. Atoms in a semiconductor hold their electrons until given small energy boosts. This occurs in photovoltaic cells that convert solar energy into electrical energy. Thin layers of semiconducting materials sandwiched together make up transistors. Transistors are the most important component in modern electronics, such as computers and cell phones.